Under the standard model of our universe, there exist two types of particles: fermions, which are the building blocks of all the matter you see around you, and bosons, which govern the fundamental forces that shape our everyday life. Photons transmit the electromagnetic force, which we can see in the form of light. W and Z bosons are responsible for the weak nuclear force, which occurs in events like radioactive decay. Gluons carry the strong nuclear force, which is what keeps your atoms together. But what about gravity? Sure, we have Newton's and Einstein's equations, but those only work when we look at the big picture, and break down when we enter the quantum mechanical realm, leaving us with the question, are there particles of gravity? Going by the standard model, it makes sense that gravity should have a subatomic particle responsible for its presence in our everyday life, which scientists call the graviton. Now, there are two previous videos on this channel from about 3 to 4 years ago explaining the basics of gravitons for those who are new to the subject. Unfortunately, since the release of both of those videos, gravitons have still not been discovered. Why is this? Well, let's start off with the obvious. Gravity is a very weak force. In fact, it is the weakest of the 4 fundamental forces of the universe. Don't believe it? Consider how a magnet is able to pin a paper to a fridge surface, or how you can lift this book off the table despite the gravity from the entire Earth's mass pulling down on these objects. Also in the past, we've discussed how we need to build such large sensors and probes to detect faint signals of stuff like gravitational waves from colliding black holes, or the warping of space due to Earth's gravity. Just imagine the difficulty we're going to face when trying to detect the effects of gravity on something as small as an electron. Keeping this in mind, would it still be possible to detect even a single graviton? To answer that, we need to go back to 2015, where scientists at LIGO detected gravitational waves. To do this, LIGO built an apparatus in which an emitted laser beam was split and each half of the laser beam was then bounced off a mirror. Then the distance each beam of light traveled in its respective direction was calculated to determine whether or not a gravitational wave had passed by and warped the space the light traveled through. The gravitational waves discovered by LIGO, an observatory with some of the most powerful and sensitive instruments on Earth, are estimated to contain about 3 × 10⁻37 gravitons. So, if we wanted to build an instrument to detect even a single graviton, then we need to build an apparatus which is 3 × 10⁻37 times more sensitive than what LIGO has, which is kind of impossible given our current technology and the fact that radiation from the environment, such as neutrino particles emitted by the sun, could prevent us from getting an accurate reading. Also, to make matters even worse, to detect an individual graviton using the described LIGO setup would in theory require mirrors so massive and heavy that they would collapse and form a black hole. Additionally, the measurements for this experiment would require an error smaller than a Planck length, the smallest possible length in the universe, which is impossible by the laws of nature. However, a simpler alternative proposed by physicists is to detect gravitons via the Gravido electric effect, which, given our technology, is perhaps the most realistic way we could detect gravitons that are passing by at a frequency of at least 10 to the 15 Hertz. The idea is simple. In the photoelectric effect, when an electron in an atom absorbs light, it gets more excited and energetic and moves away from the nucleus, and in some cases gets ejected from the atom, which we can detect. The Gravido electric effect is similar, except instead of photons, it's gravitons which are absorbed by the electron, putting it in a more energetic and excited state that we can measure. However, in order for an electron or particle to be excited by a graviton, it needs to surpass the absorption cross-section, which is basically the probability of absorbing a given particle, expressed in terms of area, with a smaller number meaning it's harder to detect, since it doesn't interact with matter as much. Neutrinos, which are famous for hardly interacting with any form of matter, have a cross-section of about 10 to the negative 45 centimeters squared. This is why trillions of neutrinos are passing through you right now without you feeling a thing. For the graviton, this area is 8 times 10 to the negative 65 centimeters squared, which means gravitons are even harder to detect than neutrinos because of how weakly they interact with matter. This is also why we have to make sure our graviton detector filters out neutrinos from the readings. In fact, because of the weakness of gravity as a force, any potentially viable solution involves sensors which are way too massive or would take billions of years before detecting even a single graviton. Due to this, unfortunately the question of whether gravitons exist or not is simply something that can't currently be answered, simply due to the lack of technology to gather evidence. But that doesn't mean that future technological breakthroughs allowing us to do so may not happen. So, let's say gravitons were discovered. What would happen? Well, it would not only be the greatest discovery in physics of all time, but would fundamentally change how scientists understand gravity on a classical and quantum mechanical level, and even open up the door to us taking a closer look at other possibilities in physics like string theory. And like any other advance in human history, the discovery of gravitons would lead to further research and development, potentially leading to technology that manipulates gravitons, which would admittedly make for an awesome utopia. Of course, despite the scientific community's deep desire to find the elusive graviton, it's important we keep an open mind regardless of whether gravitons exist or not when learning about the secrets of the universe, as anything could be a possibility. And always remember, what we want reality to be is different from what reality is. Otherwise, it wouldn't be reality. As always, don't stop exploring, and don't forget to stay tuned for more science videos.